Welcome to my channel. Today we're going to discuss something that might completely change how you think about AI. Here's a provocative thought. ChatGPT doesn't think, it searches. And remarkably, this idea is older than the internet itself. What you're seeing now illustrates this profound connection. On one side, we have classical AI search algorithms like BFS and A*, represented as a branching tree of nodes, each representing a state in a problem space. On the other side, we have modern language models, shown as a chat interface generating text. The key insight is that these two seemingly different technologies are connected by a glowing arrow, representing evolution rather than replacement. The fundamental principle is the same: explore possibilities, evaluate them, and choose the best path forward. Modern AI didn't replace classical AI, it evolved from it. This is the story we're going to uncover today.
Let's start with a fundamental question. What do A* search, game AI, and ChatGPT have in common? At first glance, these seem like completely different technologies from different eras. A* is a pathfinding algorithm from the 1970s, game AI uses decision trees and state machines, and ChatGPT is a massive neural network trained on internet data. But here's what's fascinating. They all share three core behaviors. First, they explore possibilities, examining different options and potential paths. Second, they score those options, evaluating which ones are more promising than others. And third, they pick the best path forward based on those evaluations. These three concepts, explore, score, and pick, form the backbone of intelligent behavior. Whether you're finding the shortest path through a maze, deciding the next move in a chess game, or generating the next word in a sentence, you're performing the same fundamental operation, searching through a space of possibilities using some form of evaluation function. Here's the promise of this video, and I want you to hold on to this idea. Right now, many people view large language models as some kind of magic, a mysterious black box that somehow produces intelligent responses. But by the end of this video, you'll never look at LLMs as magic again. Instead, you'll see them for what they really are: search engines with learned heuristics. The transformation happening before you represents this mental shift. We're dissolving the cloud of mystery surrounding these models to reveal the structured search mechanism underneath. When you see an LLM generating text, you'll recognize it as a tree of possibilities, where each branch represents a potential next token. Each edge has a probability score, and the neural network acts as a learned heuristic guiding which paths to explore. This reframing is powerful because it connects cutting-edge AI to decades of computer science research, and it gives us a framework for understanding where the field is heading next. Let's travel back to the era of classical AI, from the 1970s through the 1990s. This was the golden age of search algorithms. The fundamental idea was elegant: intelligence equals search plus rules. Researchers developed algorithms like breadth-first search and depth-first search to systematically explore problem spaces. Then came A*, one of the most important algorithms in AI history. A* uses the formula f of n equals g of n plus h of n. Here, g of n represents the actual cost from the start node to the current node, while h of n is the heuristic estimate of the cost to reach the goal. The magic of A* is that it combines what we know, the g value, with what we guess, the h value, to guide the search efficiently. But here's the catch. Those heuristics were handcrafted by humans. Engineers had to manually design evaluation functions for each domain, defining the state space, action space, and goal test for every problem. This approach worked, but it had significant limitations. So, why did classical AI eventually hit a wall? Three fundamental problems emerged. First, state space explosion. As problems got more complex, the number of possible states grew exponentially. What starts as a simple tree quickly becomes an overwhelming forest of possibilities. For a game like chess, there are more possible positions than atoms in the observable universe. No amount of raw computation could search through all of them. Second, manual heuristic design. Every new problem required engineers to sit down and carefully craft new evaluation functions. This was time-consuming, error-prone, and didn't scale. The heuristic that works for chess doesn't work for Go, doesn't work for protein folding, doesn't work for language. Third, domain specificity. Each AI system was essentially a one-trick pony. Deep Blue could play chess brilliantly, but couldn't do anything else. The intelligence didn't transfer between domains. This led to a famous insight that shaped the future of AI. Search worked until humans had to write the heuristics. This brings us to the bridge era, where machine learning fundamentally changed the game. Instead of writing rules like if score greater than 5, move left, or if enemy near, defend, we started training models to learn these patterns from data. The transformation was profound. Handcrafted rules were replaced by neural networks that could discover their own internal representations. The key insight here is that we didn't remove search from AI, we trained it. Machine learning models are essentially learning to approximate the heuristics that humans used to write by hand. The process follows a clear pipeline. Data flows into a training process, which produces a learned heuristic function. This function can then be used to guide decisions, just like the handcrafted heuristics of classical AI. But now, instead of encoding human knowledge manually, the model extracts patterns from massive datasets. The search is still happening, it's just guided by learned functions rather than programmed rules. Now we arrive at the aha moment. Language models are search in token space. Let me show you the mapping that makes this crystal clear. In classical AI, you have nodes in a search graph. In an LLM, the equivalent is a token sequence. Each path through the tree represents a different sequence of words. Classical AI has edges connecting nodes. In LLMs, each edge represents predicting the next token. You move from one state to another by adding a word to your sequence. Classical search uses cost functions. In language models, the cost is negative log probability. Lower probability tokens have higher cost, so the model naturally prefers more likely continuations. And finally, classical AI uses heuristics to estimate which paths are promising. In LLMs, the neural network itself is the heuristic. It's been trained on billions of tokens to learn which word combinations make sense. This is the deep insight. LLMs search through token space using learned heuristics.
Let's make this even more concrete by looking at decoding strategies. When an LLM generates text, it uses algorithms that are direct descendants of classical search. Greedy decoding is equivalent to greedy search. At each step, you simply pick the highest probability token and move forward. It's fast, taking the most obvious path, but it can miss better options that require looking ahead. Beam search is essentially pruned breadth-first search. Instead of keeping just one path, you maintain k best paths simultaneously. A beam width of 2 means you're exploring 2 promising sequences in parallel, keeping your options open. Then there's temperature, which acts as exploration control. A low temperature, like 0.1, makes the model focused and deterministic, strongly preferring high probability tokens. A high temperature, like 1.5, increases diversity, making lower probability tokens more likely to be selected. This is the equivalent of exploration versus exploitation in classical AI. The key takeaway here is profound. Inference is not generation, it's search. Here's where the story comes full circle. We're now in Era 4, and something remarkable is happening. Researchers are explicitly adding search back on top of language models. Techniques like tree of thoughts take this literally. Instead of letting the model generate a single stream of text, we build an actual search tree where each node represents a different reasoning path.
The model explores multiple approaches to a problem, evaluates which paths seem most promising, and then selects the best one. Self-consistency is another example, where we sample multiple independent reasoning chains and take a majority vote on the answer. This is essentially ensemble search over reasoning paths. Planning agents combine language models with explicit planning algorithms, using the LLM as both a world model and a heuristic function, while employing classical search techniques to find optimal action sequences. The key message here is profound. We are explicitly adding search back on top of LLMs. The circle is complete. Classical search has returned, now enhanced by the power of learned representations.
Now, let's step back and see the complete picture. We've traced an evolution spanning over 5 decades, and the pattern is remarkable. It started with BFS and DFS, basic algorithms for systematically exploring possibility spaces. Then came A-star and heuristic search, adding intelligence to decide which paths to explore first. The era of learned heuristics followed, where machine learning took over the role of designing evaluation functions. This led to large language models, essentially massive neural networks trained to predict token probabilities, serving as incredibly sophisticated heuristic functions. And now we have agents, combining LLMs with explicit planning and reasoning modules. Notice how the timeline curves back on itself. We started with explicit search algorithms, moved to implicit search hidden inside neural networks, and are now returning to explicit search augmented by neural capabilities. AI didn't move away from search, it learned how to search better. This is the central insight that reframes how we should think about artificial intelligence.
Here is the mental model I want you to take away from this video. LLMs are not reasoners. They don't think the way humans think. They don't have some mysterious form of consciousness or understanding hidden inside them. They are heuristic functions trained on the internet, guiding search through possibility space. Let that sink in for a moment. 3 key concepts define this perspective. First, heuristic. Like the H of N in A-star, the neural network provides estimates of how promising different continuations are. Second, search. Text generation is fundamentally a search process through the space of all possible token sequences. Third, possibility space. Every sentence you could possibly write exists somewhere in this vast combinatorial space, and the model navigates through it guided by its learned probabilities. This reframing is powerful because it connects modern AI to classical computer science, demystifies what these models are doing, and provides a foundation for understanding where the field is headed next. So where does this leave us for the future? 3 major directions are emerging. LLMs plus planning combines the pattern recognition of neural networks with the systematic reasoning of classical planners. Neuro-symbolic AI aims to integrate the best of learned representations with structured symbolic reasoning, and agentic systems are building autonomous agents that use language models as their core intelligence while adding explicit tools for search, memory, and planning. The common thread across all these approaches is the convergence of search and learning. Search provides the structure, the systematic exploration of possibilities. Learning provides the heuristics, the ability to recognize patterns and guide exploration efficiently. Together, they point to the next frontier of artificial intelligence. And here's my closing thought for you. The future of AI isn't bigger models, it's better search. The race isn't just about adding more parameters or training on more data. It's about finding smarter ways to navigate the vast spaces of possibilities that these models open up. If this video changed how you think about AI, please like and subscribe for more deep AI breakdowns. Thanks for watching.